In this talk, I will give an overview of the proof that the axioms of set theory, here ZFC, do not prove the continuum hypothesis. The continuum hypothesis is intuitively the statement that for every subset A of the real numbers, um, either A is countable, in other words, admits an injection into the natural numbers, or uh, R has a surjection to A. Okay, so A has at least the cardinality of the continuum R. Um, we can replace R with the power set of the naturals. It is an easy set theory exercise to show that those two things are bijective. Okay. The negation of the continuum hypothesis is the statement that um, we can find basically a set in the middle. Here, M is the middle. Um, N refers to the natural numbers. M is a set in the middle, and K is a set that it injects into a subset of the power set of the naturals. Okay, so if you unwind that longer expression, then you will see that that is indeed the negation of the first thing I said. Um, I will, in fact, unravel it even further to this longer statement. These uh, uh, English sort of sentences are shorthand for sentences in the language of set theory, which I have provided in a document in the description. Okay. Um, we will not dwell too much on this for now. I will structure the talk as follows. There will be a part C, that's where we'll start, for some combinatorics. Okay. Then there will be a part B for some details on Boolean algebras. And then there will be a part S for some set theory, and then there will be a part A to finish, which is for awesome. Okay, so part C, combinatorics. We begin with something I call the uncountable sunflower lemma, okay, also known as the delta system lemma. So here is the statement. If I have an uncountable family of finite sets, okay, so I here is uncountable, each xi is a finite set, then there exists uncountably many, okay, um is uncountably many xi's that together form a sunflower. What is a sunflower? It's the following picture. Okay, so each of these ovals stands for an xi. They all reside within a universe U, which we can think of as the union of all the xi's. Okay, and I will draw elements of the union as dots. Okay, a sunflower is one where each pairwise intersection of the ovals is the same. Okay, here it is this one dot here. I refer to the central bit as the heart of the sunflower. Okay, here is an example of something that is not a sunflower. If I had added this extra dot here, then two of the sets would have a different pairwise intersection than other pairs of sets. Okay. The proof is as follows. Okay. Um, part one, we first do one pigeonhole step. So uncountably many xi's, but countably many sizes of each xi. Remember, they're all finite, so either they're 0, 1, 2, and so forth. The pigeonhole principle tells us that there are in fact uncountably many x's of the same size, n, let's say, which is a natural number. Okay, so it suffices to show this sunflower lemma in the case that all the xi's are the same size, namely n. This is helpful because now we can induct on this parameter n. The base case, n is equal to 0, is very easy. In this case, all the xi's are empty, and so we can just take the heart to be empty. Okay, and this satisfies the definition of sunflower, right? All pairwise intersections of empty sets is an empty set. Now we use induction. So we want to show the case for xi all of size n plus 1, perhaps assuming previous cases. Okay, so case one is if there exists a dot um, in the universe, U, in uncountably many xi's. Okay, if that is the case, then all we need to do is look at that family of xi's, remove the common dot from all of them, and then we get sets of size n. Okay, so then we can use the induction hypothesis to get a heart um, for that family of sets, and then we can just define for the n plus 1 sized family um, to be that heart union the extra dot. Okay, so um, that is going to be the heart of the n plus 1 sunflowers. Case 2, well, the opposite of case 1 is otherwise. Okay, otherwise, uh, every dot in the universe has at most countably many xi's containing it. Okay. This tells us in particular that for every xi, okay, because each xi only has finitely many dots, and each of those dots only has countably many things touching it, um, there are at most countably many xj's who intersect with xi. Okay, that's my symbol for intersect with. Um, so we can construct the uncountable family as follows. So we start with x0. Okay, there are countably many things that touch it, so we could just throw those away. The original family we started with was uncountable, so there are uncountable many things remaining. Okay, so we just choose another one, xi, from that remaining bit. Okay, again, only countably many things are touching it. Throw those away, or uncountably things left. So we can just keep doing this. Okay, so iteratively choose one from the remaining family, okay, and then throw away all the other countably many sets that touch it. Okay, and if we continue this process transfinitely, um, or you can think of it as Zorn's lemma, then we indeed produce an uncountable family of, in this case, disjoint sets. Okay, an uncountable family of disjoint sets. So in case two, we will get an sort of a degenerate sunflower where the heart is empty and it's just petals. Okay, so hopefully that lemma made sense. The next thing we are going to prove um, or work with will be open subsets of 2 to the k times n. Okay, the reason I work with k times n instead of just a regular set k here is arbitrary. Any set you can imagine is because that will come up later. Okay, so that is actually not important here, but it will show up later. So first, what are elements of this uh, product set, product space? Well, elements are 0, 1 tables. Okay, so tables, which we can draw by the following. The horizontal axis is k, vertical axis is the natural numbers n. Okay, and then in every spot there may be a 0 or a 1. Okay. There are, of course, infinitely many spots. I won't draw them all, but that is what an element of 2 to the k times n looks like. Okay. I will use the following notation, star notation. Here's a simple example of a star notation. When I write 0 star, that refers to any string 0 made of zeros and ones of that form. Okay, so this is the set containing all strings of the form 0 star. In other words, 0, 0 or 0, 1. Okay, so when I have a star, that refers to a subset. Here it refers to the subset of 2 to the 2. Okay, so we define finitely determined sets. These are subsets of 2 to the k times n by a partial function which has a finite domain from k times n to 2, where 2 here refers to the set 0 and 1. Okay, so we have finitely many zeros and ones scattered around this big table. Okay, and the rest is stars. Okay, and this refers to a subset of 2 to the k times n. A special type of finitely determined set, which will come up later, is called U sub k comma n, where k is an element of capital K, n is an element of capital N. This refers to, we could abbreviate them with a 1 or a 0 in the superscript. These refer to the subsets in which on the kth column and nth row of this k by n table, there is a 1 or a 0, if indicated by the subscript, where everything else is a star. Okay, so again, this is a subset of 2 to the k times n. And general finitely determined findet sets are intersections. Okay, so these are intersections, finite intersections of the UKNs. Okay, we define open subsets of 2 to the k times n as arbitrary unions of findet sets. Okay, and closed sets, here's one criterion: if they are a arbitrary intersection of, let's say, finite unions of findet sets. Okay, this will come up later. Okay, very well. Here is an example. So fix k not equal to L in capital K. I claim the set of 0, 1 tables with column K equals to column L, which we can visualize as follows. Here I have column K, here I have column L, and it's filled with zeros and ones because it is a 0, 1 table, and it so happens that the columns are identical. Well, clearly this set, which is a subset of 2 to the k times n, is non-empty. Okay, it is definitely possible to fill in the table with zeros and ones in a way that column K and column L are equal. Okay, we can write it as the countable intersection of the following findet sets. Okay, I have K, L, N, I have a 1 and a 1, and everywhere else is a star. Union K, L, and 0, 0. Everywhere else is a star. Okay, so I'll leave it to you to check that indeed this equality is true. Okay, and observe that by this is a closed subset of 2 to the k times n. Okay, and moreover, I claim the following interesting property. Okay, these are just to practice our notions of open and closed, and also because this thing will come up later, I claim that this does not contain, okay, it is not a superset of any finitely determined set. Okay, and the proof of this is pretty easy. Okay, consider an arbitrary findet set, which I'll just draw as follows. I have some zeros and ones scattered around. Okay, perhaps some in column K, some in column L. Okay, that's all fine. But notably, there are only finitely many ones and zeros. So because each column is infinite, okay, it is a copy of n, there are definitely going to be places that are stars. Okay, so I can just choose those stars to be anything I want. For instance, this empty space here, okay, I could choose to be a 0, and the corresponding spot in the other column, which I chose to be empty, okay, I choose to be a 1. Okay, now this and everything else I can fill with zeros and ones arbitrarily. Okay, whatever. Now this is going to be an element of the findet set I had started with, okay, that I had drawn initially. But clearly this is not going to be in this set. Okay, so what I have shown is that for any findet set you give me, not every element of it, not every 0, 1 table inside of it will be an element of this. Okay, so this proves this interesting observation. Okay, now, what does this have to do with the Sunflower Lemma I just proved? Well, uh, I claim the following. Okay, so claim uh, if I have ui, I indexed by capital I, uncountable family of opens. Okay, that's why I spent so long defining opens. Um, then there must be some that are not disjoint. Some pair, let's say, that are not disjoint. You can think of the contrapositive as this, as asserting that if I have a family of pairwise disjoint opens, then that family must be countable. Okay. Um, you should think in your head of open subsets of R. So think or have an analogy to open subsets of R. Okay. Um, there you have a elementary real analysis exercise that every open set contains a rational. And so if you have disjoint open sets, then you can only have at most countably many of them. Okay. But in fact, um, this theorem is true for opens in 2 to the k times n for any infinite set k. Okay. All right, so what's the proof? The proof is as follows. Okay. Um, First, let's think. Well, okay. First, let's make a reduction. So each open, I told you before that the definition of open is something that is an arbitrary union of these findet sets. Okay, we can define the notation uh, given a partial function f, p from k times n to 2. Let me notate it by this partial arrow. We can define the notation u p to be this subset. Okay, so in other words, the set of all extensions of all functions, total functions, not partial functions, extending the partial function p. Okay, that idea of function extension is the same as this star notation I set up previously. Okay, so if we define up in that way, every ui must contain some upi. Okay, it must contain some findet set determined by the finite domain function p sub I. Okay, where p sub I is a finite domain function from k cross n dash dash 2. Okay. Well, what does it mean for UPI intersect UPJ to be empty? That means there is no function that extends both. And the only way that can happen is if domain of PI intersects with domain of PJ. And moreover, at a point common to their domains, P sub I at that point is different from P sub J. Okay, that's the only possible way that the intersection of these two UPIs can be empty. I'll leave it to you to think through that. Okay. All right. So now, perhaps you see where this is going. DOM PI is a finite set indexed by I. And so by the Sunflower Lemma from previously, there exists uncountably many P sub I whose domains pairwise intersect to equal some part, okay, which is a finite subset of k times n. Okay, so we have some part here, and everybody else is forming a sunflower around this part. Okay. So the green ovals I just drew refer to the domains of P sub I. All right. Well, I claim that if I have uncountably many P sub i's, um, I only have finitely many functions from heart to 2. Okay, so again, by pigeonhole, there must be uncountably many P sub i's um, whose restriction to heart, which again is the only place where all these P sub i's intersect, um, is the same. So matches some one of those finitely many functions from heart to 2. Okay, but in this case, all those P sub i's will have common extensions. Okay, they'll have common extensions. So in fact, not only do we have some pair of u sub pi and u sub pj that intersect, we have in fact uncountably many pairs u sub pi and u sub pj that um, that intersect. Okay, so we will come back to this much later, but for now, just keep in mind this countable disjoint opens property in 2 to the k times n. All right, so that concludes the combinatorics section. Part B, Boolean algebras. Okay, the canonical example of a Boolean algebra we should think of is the power set of a space S. Okay, so space S. Okay, what operations can we do for elements of B, in other words, subsets of S? We have a subset operation. Okay, we have a minimal element with respect to the subset order, partial order, um, which is the empty set. And we have a maximal element, which we call respectively 0b and 1b. Okay, so 1b here refers to the total space S, and that is the maximal element. Okay, everything is a subset of S. And we also have a complement operation. Okay, so B complement would be equal to S minus B. Okay. Um, Often for this talk, I will use the color green to talk about the Boolean algebra. Okay, so if you see a green one, especially a green one with a B subscript, that will refer to um, this maximal element of the Boolean algebra. Okay, not the number one, not any other thing, the actual maximal element of the Boolean algebra. Okay. Um, Now, what is important about this subset operation, it is that it has the infimum. Okay, in other words, greatest lower bound, which is given by the intersection. Okay, so if I have any family of subsets of S, their greatest lower bound in this lattice partial order will be given by the intersection. Okay, and we also have a union, which is the sup or the least upper bound. Okay, and moreover, these intersections and unions satisfy lots of properties. For example, for all B in B, B union the negation, sorry, the complement of B is equal to 1B. Okay, and B intersect B complement is 0B. Fine. And we also have some distributivity properties. Okay, so A intersect B union C is equal to A intersect B union A intersect C. Okay, and lots more. You can just Google Boolean algebra and you'll see a whole list of examples. Okay. For the purposes of this talk, I'll actually have an extra notation. B fat double arrow B prime is defined to be B complement union B B prime. Okay, I will talk more about this in a moment. But a fact, exercise to get used to this notation. B, I'll say implies B prime is equal to 1B if and only if B is less than or equal to B prime. Okay, B is a subset of B prime. so play around with that. There is another Boolean algebra that I need to tell you about. By the way, in my discussion of the greatest lower bounds and least upper bounds, I'm already basically assuming or setting up the notation for complete Boolean algebras. Okay. And the next example is also an example of a complete Boolean algebra. Okay, so this example is the regular open subsets of a space S. Now think of S as R or R squared for the time being. Okay, so picture S as R or R squared. What is RO? These are the regular opens. Okay, where set U, open set, is called regular open if and only if the closure and then interior of U is equal to U. Okay, so example 1, comma 2 union 2, comma 3, which is an open subset of R, is not regular open because the closure of this thing is equal to 1, 3 inclusive, and the interior of that is equal to 1, 3. Okay, so this is distinct from what we started with, and so it's not regular open. Okay. But in more, generally, you should think of a regular open subset as an open set, which sort of doesn't have any punctures or rips, right? So if I have R squared and I delete, let's say, an interval inside of it, then the closure of it would fill in the interval, that rip, okay, and the interior would not take that away. Okay, so regular open sets you can think of as open sets without rips or holes. Okay. Of course, if there was a big hole, okay, so imagine this annulus, yeah, the hole is too big, taking the closure would not help, okay, patch the hole. So tiny punctures, okay, bullet holes. If somebody shot a cannonball through the open set, then unfortunately it's not going to recover. Okay. All right. I claim that this set of regular opens actually forms a Boolean algebra. Okay, so again, we have a subset operation. We have 0b, 1b. Here is empty set, and again is S. Okay, and in fact, the greatest lower bound we can prove as a theorem. Okay, so theorem. Let me define this funny notation. So weird intersection symbol b sub I. Defined to be the intersection of b sub I, the classical set theoretic intersection, closure intersection. Okay, we define that actually is the greatest lower bound of bi. Okay, why is that true? So proof, suppose that U, which is regular open, okay, it's an element of B, is a lower bound of bi. So in other words, U is a subset of bi for all I. Okay. Then U is a subset of the intersection of the bi's. Okay, and that's just classical set theory. And now we use monotonicity properties. Okay, if I have this inequality, then taking closures of both sides preserves the inequality. Taking interiors of both sides preserves the inequality. Okay, but U closure interior is precisely equal to U because it's regular open. Okay, and so indeed this set here, which we defined using this funny notation above, is in fact the greatest of the lower bounds. Okay, that is what we wanted to show. Great. I will not check the rest of the Boolean algebra axioms, okay, distributivity, blah, 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 but I will leave that to you. Okay. Moving on. Okay, so the summary of that section was, remember, there's this thing called power set of a space S. It has a lot of properties, namely those of a complete Boolean algebra. And surprisingly, there is also a subset of that space, subset of that complete Boolean algebra called the regular open Boolean algebra. And that also happens to be complete. Okay, so that's all you need to take away from that section. And before we go from CB to A, we take a detour to part S. Okay. All right, some set theory. Great. So what do I want you to know about set theory? There's not too much time, so here is what I've condensed it to. Okay, so some examples of sets we care about. Okay, so we start with the empty set. Okay, everybody has to care about the empty set. That's the foundation of our whole entire theory. Okay, I draw it as this empty box. Okay, and also sometimes denote it with the symbol 0. Okay, so if it's a black 0, that refers to the set, empty set. Okay, if it's a green 0, then that refers to the element of the complete Boolean algebra from above. Okay. We can also take the set containing the empty set, which we draw as this box. Okay, so it's definitely not the same thing as 0. This thing we call 1. Okay. And we can take this set, which we can draw as this. Okay. And this we call 2. Okay. The way I'm forming these sets, by the way, is what I do is I take all the elements of the previous one. So the previous set I had an empty and also a box within a box. And then I just take a copy of that original, that whole thing. I just copy and paste that guy. All right. And that is 3. Okay. By the way, if you look on Wikipedia, this is called the successor operation. Okay. I will not define it rigorously, but with the boxes, hopefully it is understandable. Okay. Now we have all of those sets. We can create the set of natural numbers, sometimes denoted by omega, also sometimes denoted with capital N, boldface N. This is the set 0, 1, 2, 3, and so forth, which we can draw as a box as follows. Okay, and so forth. Okay. Now, from this sort of basic collection of sets, we can form more complicated sets, in particular the ordered pair. Okay, so these will be extremely important because we will eventually be talking about functions. So when I write the symbol parentheses a comma b, what I really mean is the set described as follows. Okay, so the picture is this. And this is a slightly weird different definition. It's due to Kuratowski. Okay. And all we need this definition to satisfy is that if A, B is equal to C, D, that is the same thing as A equals C and B equals D. Okay, so you can, this is actually one of the first, shortest theorems of ZFC. Okay, so this is an example of a statement of set theory. Okay. Slightly more formally, we can write P is pair AB as follows. We can write it as for all C in P, for all components of the pair, either C is equal to A or C is equal to A, B. And these we can formalize even in more detail as, for instance, A in C, and for all X in C, X is equal to A. Okay. I leave it as an exercise for you to formalize this one. Okay, and then an example theorem of ZFC, provable from the axioms, is for all PQ, A, B, C, D, P is pair A, B, and Q is pair C, D, if and only if A is equal to C and B is equal to D. Okay, so that is an example sentence of set theory that is provable from the axioms. Okay. Okay. And we can furthermore say stuff like P is pair. Exists, we can define this to be exists A and B, so that P is pair AB. Okay. For later, it will actually be slightly important that the quantifiers are bounded. Okay, so the quantifiers I've written down are not bounded, but we can easily fix this and create something that is bounded. Okay, so here's an example version of is pair that is bounded. P is pair, we can define to be there exists a component in P, okay, and there exists A and B in C, so that P is pair AB. Okay, and these are bounded because the quantifier is not just exists A, it exists, okay. It's not just exists A, it exists A in C, okay, which is something, this is another set, okay, just not ranging over everything, but rather ranging over just a set. Okay, um, I'll speak more about bounded quantifiers and why we care about that in a moment. Okay, now, um, from pairs, we can define functions, right? So f is a function from, let's say, domain D to C. If, there are lots of ways to formalize this, but here's an example. For all P and F, P is pair from D to C, right? We can formalize this using P is pair from D to C by using more bounded quantifiers. So here's another example. A is in the domain D. There exists B in the codomain C, so that P is pair AB. Okay, so that's an example. And for all P and Q, same first coordinate implies P equals Q. Okay, and I'll leave it as an exercise for you to write this in the language of set theory. Okay, so something for all, something exists. Okay, something in, something equals, blah, blah, blah. And extra challenge, write this in a way that all the quantifiers used are bounded. Okay. I have written it in the supplemental notes found in the description. But if you're interested, try it yourself. Okay. So uh, the takeaway from this section is we have a bunch of building blocks. Okay, we start with 0 and then we build up. Okay. Then we can build further structures like ordered pairs and functions and so forth, where everything is eventually expressed just in terms of the language of set theory, okay, which all the symbols are as you see them for all in, if and only if, equals, etc., etc. Okay, great. Let's continue. Now, I will introduce a slight variant of this, okay, which brings in the Boolean algebras. So fix a Boolean algebra, complete Boolean algebra. Okay. And now I will introduce something called a B tag set, or for short, B set. Okay. So the idea is as follows. Take any set from the previous page. Okay, for example, the set 1. Okay. We leave the outer box unchanged. So if we had started with instead the empty set, we just don't do anything because the outer box is all there is. We always leave the outer box unchanged. And the inner box we tag with an element of capital B. Okay. What does that mean? We can encode this as the following set. The set of empty set, which refers to this black box there, right? The inner empty box, comma, B. Okay. So let's do some examples. So we have, let me call this curly U. This will be the set 0 tagged with the interval 0 to 4, where the Boolean algebra here we'll be working with is pow r, and the interval 0 to 3 is an element of pow r. Okay. And we can, again, cook up something similar. Okay, let's cook up something based on the number 2. Okay, so let's call this 0, 4, 1, 5, and 1, 3. Great. What does this all mean, right? What is the point of doing this tagging? The idea is we should think of this as a location varying set. Okay, so here is some definition. Okay, so for S in the space S, which happens to be R in our case, this is a specific location, we can define the evaluation at S. Okay, so U, curly U, evaluated at S, we define as follows. We go through, and if S, the location, is in the tag, then we keep the box. Okay, the box is considered on. Um, or if S is not in the tag, then we consider the box off and we forget about it. Okay, so for example, U sub 1, 1 is inside the interval 0 to 4, so it stays on. Okay, so it's interpreted as 1. Okay, but U of 10, on the other hand, 10 is outside of the interval 0 to 4, and so the box is turned off. In other words, it's invisible to us, so we don't see it. So U becomes the empty set, or in other words, 0. Okay. Think of it a little like how some websites, Netflix or whatever, depend on where you are. So if you are, for instance, in America, you will see one version of the website Netflix. But if you're in, France or something, you'll see a different version of Netflix. Okay, so these tags, these B tags, refer to a location where you're sort of seeing different phenomena, different sides of this B set. Okay. Um, so here's a more complete analysis of this curly U. Okay. So there are two behaviors. For S in 0 to 4, then this evaluates to the set 1, which is box within a box. And outside of 0, 4, it evaluates to 0. Okay. And let's do a complete analysis of V as well. Okay, so V here has three behaviors actually. Okay, you are free to pause the video and work it out yourself. Here are the answers I got to. I could be wrong. If S is in 1 to 3, then it evaluates to 2. Okay, it evaluates to this sort of picture. And for S in 0 to 1, with the bracket like that, union bracket 3 comma 5 parentheses, I think it should evaluate to 1. Okay, so please check that. And if it's not in 0 to 5, then it just evaluates to 0. Okay, fine. Now we define these funny notations as follows. So bracket U in V, this refers to the set of all places S in S, so that the evaluations US is an element of V sub S. Okay, so in other words, this is an element of B, okay, and it refers to a region, okay, at which you see that U is a subset of, sorry, not a subset, U is an element of V, okay. And similarly, we can have U equals V is defined in a similar sort of way, but with an equal sign instead of an element. Okay. So what are those? Okay, again, I leave it to you to think a little bit. Here are the answers I got. So I got that this is equal to 1 comma 3 union 4 5. Maybe some brackets are a little off. Whereas the equals, that holds on the locations 3 to 4 and the complement of 0 5. Okay, so that little negation symbol refers to complement. Here they're both 1, and here they're both 0. Okay, so it's a little weird. Okay, you have two entities, a B tagged, a B set U, a B set V. And in some locations, some regions, in Canada, it happens that U is an element of V, but elsewhere, right, in Zimbabwe, it happens that U is equal to V. Okay, so things like these basic atomic logical formulas can change depending on where you are in B. Okay, and you can think of these as functions from the set of B tag B sets squared to B. Okay, if you are familiar with set theory, this doesn't actually make sense because this is what is called a proper class. But the way around this is actually that we have a formula. Okay, so we will have a formula in the language of set theory called is, let's say, tagged set U with parameter B and is equal to some very lengthy formula. Okay, much like is pair, which I introduced above. Okay, but of course, is tag set would be longer. Okay. And then we will have u v, let's say, in where little b refers to this idea that u in v should equal b. Okay. So there is a way of defining these formulas, these expressions, very similar in spirit to is pair above, um, that give you these sort of functions, quote unquote functions. Okay, that's just a minor technicality. Okay, now let's continue to work up our complexity here. So I introduced um, these taggings of tagged versions of 1 and 2. There is, in fact, a more canonical way of associating tagged sets to regular sets. So if I have a set, um, like this, with a lot of stuff in it, then what I can do, u, then I can form u dot or u check, okay, to be, I have the big box, the outer box, which again, remember, I do nothing with, and then all the inner boxes and all of the boxes within those, um, et cetera, I label with 1, okay, where green 1, again, refers to the maximal element of the Boolean algebra, not to, the set 1 that I drew in black above. Okay, so for every inner box, okay, you just keep diving inside and you label them with 1s. And you should think of these as location um, sort of invariant or deterministic. That's where this whole location, seeing different things at different places phenomenon doesn't exist because um, any uh, any location S will open all the boxes. Okay, so you'll see just the same thing each time. I lied a little bit. In the examples I have above, we work pointwise. Okay, so we work on points, S, little s. Um, the whole theory actually is more general than just working with B is equal to pow of S, capital S. It works with any complete Boolean algebra. But for those, you need to be a lot more careful in how you define the appropriate things because you cannot talk about points anymore. But I will leave that to uh, the book. Okay, so I'm following a book by Bell. I'll link it in the description. Okay, the key intuitions are exactly those of what happens pointwise, anyways. Okay, and that is what I want to impart on you. So again, let me bring up the idea of uh, encoding these B sets as sets we are familiar with. Okay, so for instance, this guy you should think of as the set containing one pair, empty set comma 0, 4. So this is an element of B. Okay, and then I have another thing who is tagged by 1.5, sorry, 1 comma 5. And what should go in this spot? Well, it's the set um, containing empty set, comma, 1, 3. Okay, so this black box here is this black box here. Okay, so at the end of the day, it's all just regular sets. Okay, this is not like a radically new thing, but what I've basically done is we have these B sets, um, which you can think of as functions from the space of B sets, the class or whatever of B sets to B. Okay, so we can think of this as the function which takes in the empty set and this thingy, which happens to be a B set, and maps those respectively to 0, 4, okay, and 1, 5. Okay, so when I refer to these sets as functions, this is what I mean. Okay, set theoretically in the sort of classical encoding of these objects, they are actually functions. Okay. All right. Let's continue on. So I've introduced this check operation. which all you do is, again, slap ones everywhere. Slap the tag one, one sub b everywhere. Um, okay. And finally, for b sets u and v, let's say, I'm going to introduce the notion of an ordered pair. Okay, so uv, curly u, curly v, I'm going to put a check on the bracket to emphasize that this is an ordered pair as a b set. Okay, an ordered set in the normal way would just be something that is this. Okay, but this is not a B set because, for instance, this box does not have a tag. Okay, and in fact, U itself, which remember has an outer box and some stuff in it with green tags. Okay, U itself also doesn't have a tag. So the way we fix this is just put a tag one everywhere where we need it. Okay, so a total of 5 extra ones. Okay, so that is what I mean by ordered check. Okay. So if I have, again, B sets U and V, an ordered pair checkified refers to this construction. Okay. And all right. Now let's keep going. We have already this bracket operation defined for these atomic formulas U in V and U equals V. I will now assert that we can build these for more complicated formulas. Okay, so let's do an example. So let's again focus on is pair. So P is paired, AB, which remember is this formula from above. Just copy it. And now what I will do is I will consider the following. So let me define this to be curly P, and I'm going to write this mysterious expression. So curly P is pair curly U, curly V. What on earth do I mean by that? What I mean is I slap brackets to this whole expression. Okay, so I'll slap brackets to this whole expression. And then I use the following syntactic rules on this thing. So if I see a for all C and P, I will replace this with a Boolean intersection over all C in the domain of P. So again, think back to curly P is a function, okay, and C here is curly. Both of these are B sets. Okay. And then let's expand this expression. We're at this stage. Okay. I'll discuss the rest in a moment. We can now use the following rule to write this. Bracket of an and is equal to intersection of brackets. So I'll write it like this. Okay. So this thing is equal to copy, paste, bracket here, and replace this symbol with the Boolean operation and. Okay, Boolean intersection. Okay, and again, how do I do that? Well, I always turn a for all into an intersection, x, curly x in domain of curly C of x is equal to u. Okay. Unfortunately, I've messed up a couple of these letters. I think you are able to fix them on your own, but I have done so here. Okay. And this or will turn into a Boolean or, and then we can continue like that. Okay. So the point is, by expanding out using syntactic rules, I can convert this weird looking expression into things based on the bracket of in and the bracket of equals that we have already defined before. and also these Boolean operations. Okay, so again, let's type check everything. This guy is an element of B. This guy is an element of B. B intersection over elements of B is also in B, and so forth. So everybody here is going to be an element of B. Okay. Um, and now I will state a theorem. Okay, so couple theorems. If phi, okay, a sentence in the language of set theory is an axiom of ZFC, so go on Wikipedia or other sources and look up axioms of ZFC, you'll see it all written out. They're even not too long, okay? You can understand even the most complicated of them if you just sit down and think, for a couple minutes. Phi is an axiom of ZFC, then bracket phi, which again is defined in this sort of inductive procedure, where all for alls will turn into Boolean intersections and so forth, then this thing will evaluate to 1b. Okay. In other words, the axiom of set theory hold everywhere. And intuitively, this should be true because, at least when we think pointwise, um, pointwise, at every point, well, what do we see? It's just normal sets. Okay, so at every point when we do the evaluation, it's just normal sets. And normal in, okay, that's how it was defined, and normal equals. Okay. And for normal sets, um, they satisfy the axioms of set theory, ZFC. And so we should expect that the axioms of set theory do in fact hold everywhere. Okay. Um, when we're not allowed to work pointwise, okay, and so this definition doesn't work. Let me again emphasize that this is the definition for B is equal to pow S, where we can work pointwise. Um, in that setting, um, this should be very intuitive. Should think about the definitions enough so that the statement becomes natural. Um, it's slightly harder to prove it when B is a complete, an arbitrary complete Boolean algebra. But honestly, the proofs are not that long. Okay, so I've linked resources in the description. So that's the first theorem. The second theorem is called soundness, which says that if phi can be deduced um, from the axioms, let's say, um, by logical operations, for example, modus ponens, right? If you have, for instance, phi to hold everywhere, and also phi implies psi holds everywhere, where this thing, I'll just point out, uses the funny arrow we defined previously, okay, which remember is this thing complement Boolean or um, in this way, then we actually get that psi holds everywhere. Okay. If phi can be deduced from the axioms in a logical way, then phi also holds everywhere. Okay, so maybe I said that a little wrong or a little clumsily, but that is what I mean. Okay, so in fact, not only is ZFC holding everywhere, all the consequences, all the theorems, all the things that can be proven um, using the logical rules of deduction um, uh, do also hold everywhere. Okay. And finally, here is one thing that is going back to what I said about bounded quantifier formulas. If phi x holds, then bracket phi of x check dot 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 xn check holds with probability. Sorry, holds everywhere. Okay. Sometimes people use the words with probability 1. Okay. There is in fact a decent analogy with probability theory and holding almost everywhere. Okay. But I will not say more about that. So this type of theorem, where phi is bounded quantifiers, only has bounded quantifiers, is useful for stuff like checking that, a pair is actually a pair. Um, I will assert that um, this thing actually evaluates to 1. Okay, this thing evaluates to 1. Maybe I'll do a little bit of a check for you. I think it's good to see that. Okay, so let me give myself a little space. Here is the type of things that we need to check. Okay, so for C in the domain of P, well, we know what P is explicitly, right? So P is this thing. So what does it mean to be in the domain of P? Well, that means that C is either equal to the black box U, which comes with a 1 inside, or C is equal to UV, where both of those come with 1s. Okay. We'll just focus on this first thing. It turns out that this second one will be useful for this situation up here. Okay. Well, if C is equal to U1 in a box, then it turns out that U in C, if you just go back through the definitions, this is equal to 1. Okay, great. And furthermore, X in domain C, well, that only has one possibility. That means X is equal to curly U. Curly X is equal to curly U. Okay. And then this thing also holds. This thing is also equal to 1. Okay. Maybe I'll color them in green to emphasize that they're 1 in the Boolean algebra. Okay. And the intersection over 1 is also 1. Okay. And 1 intersect with 1. Okay. 1 intersect with 1 is equal to 1. Okay. So this whole thing is equal to 1. And it turns out that this thing will also equal to 1. And so 1 union 1 will be 1. And that will hold for both C's. Okay. And so this whole thing will evaluate to 1. Okay. Hopefully that gave you a sense of how these things are deduced. Okay. The next part is the finale. Okay, so part A for awesome. Finally, we do the continuum. We approach the continuum hypothesis. Okay. So for this, let B is equal to pow to the k times n. This will in fact change, but let me keep it here for now. Okay. Again, k is any set. Okay. And basically in this section, we are trying to prove that k is an injection, or there is an injection to let's say, the power set of the naturals. Okay. Keep that in mind. Okay, that is sort of roughly what we're doing. So let me remind you what u sub kn is. This is a subset of 2 to the k times n, defined by the 0, 1 star table, 1 in kn, and stars everywhere else. Okay, we define the B set as follows. Okay, so again, let me emphasize B is in green. So gk dot, where k is an element of capital K. The dot is to remind us that this is actually a B tag set. This is defined as the following thing. So I have 0 or 0 check. Okay, and this is tagged with UK0. Okay. I have 1 check. Okay, so this thing is 1 check. And it's tagged with UK1. And then I have 2 check. Okay, let me just draw it out for you. So 1, 1, 1. That's what 2 check is, remember? And then I have UK2, and so forth. Okay, so written out a little more succinctly, it's this. Okay, so the two things I've written are identical. And it turns out that one can show that GK dot, as described like this, is a subset of the natural numbers. Okay, just write it like that. Holds everywhere. Okay. The intuition is that for every S, every element of this space 2 to the k times n, which remember is a 0, 1 table. Okay, when I evaluate this, if S is inside of this thing, then that turns 0 on. Okay. And if it's not, then 0 remains off. Okay. So of these sets 0, 1, 2, 3, 4, and so on, some of them will be turned on based on the details of the 0, 1 table little s, and some of them will be turned off. But either way, we will still be describing a subset of the natural numbers. Okay. This formula here isn't a sentence in the language of set theory. See the description for more details. And then, by expanding out that formula in terms of for alls and exists and ands and so forth, and checking and boiling this bracket down into the in and the equals, which were defined above, you can in fact check in a similar sort of way as before that um, that this thing holds everywhere. Okay, so GK is a subset of N, holds everywhere. Okay, and now we can define pairs. K check, GK dot check. Okay, remember what does that heinous notation mean? That means that I have K check there. I have K check, GK dot. Okay. Where again, that comes with a 1, 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 and that comes with a 1. Okay. And then one can show that this dude, I'm not going to write it again, is a pair, holds everywhere. Okay, so again, it should be obvious if you think about it pointwise. Okay, so if you fix a a 0, 1 table and you evaluate this thing pointwise at S, then it is indeed a pair. Okay, and that is true everywhere, and so this thing holds equals to 1. Okay, great. And now we define F. Okay, so F is defined to be the set of all of these things. So the set of all of these things for all k and capital K. Okay. So in a sort of slightly more familiar notation, perhaps it's this. Okay, so F is this set. Where actually I lied a little bit. It's this comma 1 as a function, right? So let me use maybe a different color. F is equal to this whole thing here. I put an extra 1 on each sort of b-tagged pair. Okay. And finally, what does this thing satisfy? This thing satisfies f is a function from k check, capital K check, my bad, capital K check, to Pn, and Pn is, let me say it like this, to S, where S is a subset of Pao n. Okay. Again, that's one of these formulas, expressions in the language of set theory that are in the document. Okay. So you can imagine, or hopefully it is intuitive that this sort of thing is true, right? If you look at this thing, this is essentially, if you ignore all the tags, most of them are 1 anyways, so it's okay to ignore them, at least on an intuitive level. This is just a set of pairs, right? K, comma G. And so this is as this statement shows, it is a function from K to the power set, right? Every little k will map to a subset of the natural numbers. Okay. And now the claim is that f is, in fact, an injection from k check to Pn or to S. Okay, let's call it S everywhere. Okay. Or in other words, f is not an injection, holds nowhere. Okay. So hopefully that switcheroo didn't make you too confused. What does not injection mean? That means that there exists a k and an L in k. Okay. So that k is not L, and f of k is equal to f of L. So that's what that means. And how do we expand that out? Remember, bracket with an exists becomes a Boolean or, Boolean union, over k and L in k, k not equal to L. Technically speaking, I should be putting checks over all of them. Okay. Inside of here, they refer to, maybe I should be putting checks over them as well. Okay. All right. This is equal to this whole thing. That deals with that part of the expression. Okay. And now I'm going to put in gk dot is equal to gl dot. Okay. What is that? Well, where does, for, if we think pointwise, for what points, for what elements, for what 0, 1 tables, what 0, 1 tables will satisfy gk dot equals gl dot? Well, that's exactly if column k equals column L. Okay. If you remember, I started section part C, the first part of this talk with this example. Okay. This is equal to, we can think of this as equal to, for all n in n, n in gk dot, can put some checks, n in gl dot, or, right, wrong or, Boolean or, b or, the same thing but with not equals, not in. Okay, so you can fill in the dots there. Okay, and this here, by definition, okay, was equal to ukn, and this here was equal to uln. Okay. So this is exactly this this thing I drew up here. Okay. Okay. So please review that section as needed. I know it was forever ago. But anyways, this is equal to, let me clarify what I'm talking about here. This whole thing is equal to the set of 0, 1 tables such that there exists k not equal to L with column k equals column L. Okay. Now, here is the very strange idea. Okay. Here is, observe the following. Okay, for, let's say, capital K very large, think power set of n. Okay, we allow that to happen. Every 0, 1 table, okay, there are the tables are very, very, very long. Okay, all of these tables will necessarily have two columns that agree. Okay, for capital K as large as pow pow n. Okay, And so this would actually turn out to be 1b, which is not what we want. Okay. But the devious trick is as follows. The devious trick is we take b to be Rho of 2 to the k times n instead of pow. Okay. So the Boolean intersection is actually equal to the regular intersection, complement intersection. Sorry, no, Jesus Christ. Closure interior. Okay. So when we look back at this, okay, everywhere we are taking the closure and the interior, including here. So we do this here as well. Okay. Right. Okay. But from what I said in part C, this is a closed set. It has empty interior. And so this whole thing actually equals 0. And so this thing actually ends up being the countable union. Sorry, definitely not countable. The arbitrary union, the K union of 0, which is 0. Okay. So just by choosing the Boolean algebra to be different, we have somehow got the opposite conclusion. So we started out with 1b, and now we end up with 0b. Okay. And 0b is exactly what we want, right? We wanted this original statement. So I consider this to be just a devious trick, the switcheroo of which Boolean algebra to use. Of course, this Boolean algebra doesn't actually have points. Okay, in fact, that is what saved us. And so all the pointwise reasoning we did above doesn't actually hold. But a couple of pages of the textbook will fix that issue. Okay. This shows that we do, in fact, have an injective function, essentially, from K, capital K, to a subset of pow n. Okay. We're not done, because if you recall from the very, very beginning of the talk, that is just one bit of the situation, right? So we've successfully, or I've given an overview of how we sort of get that part, but we also have this non-surjectivity statement, right? And it turns out that that's actually not too bad. The tools I have set up in part C of the talk, which, if you were keeping track, I have not used yet, or I haven't used all of it yet, will now show up. Okay, so this is finale for the non-surjectivity, and then we'll be done. So let's fix sets, arbitrary sets, any sets, Z and A. Okay, with cardinalities satisfying that A cross N. If you have done any set theory, you will know that this is A for A and Z infinite. Okay, but we actually don't need to think about that. With cardinality A cross N strictly less than that of Z. Okay. Of course, you can always find such Z and A. Okay. The universe of sets is very big. You can just keep going up. We want to show that there exists H. Okay. Let me just call it F, because I just use the letter F for functions, such that F is a function from A check to Z check, and F is surjective to be 0. Okay. So things that were not surjective before still are not surjective here. Okay. And that will give us the statements we need. Okay, because all we need to do is we can take K very, very, very large, and then some guy in the middle, okay, large enough so that these sort of cardinality inequalities hold, and then we will get a the desired non-surjectivity statement. Okay, so I leave it to you to actually think through why this is exactly what we need. Okay, for in fact both of these statements, right? So I have two non-surjectivity statements. Doesn't exist H1 and doesn't exist H2. I claim that this last part, this A and Z business, will accomplish that. Okay, accomplish both of those. Okay. So I claim that this statement is implied by for all. Well, let me say it this way. This is equal to a Boolean union over all f. Okay, here it's not quantified, so I'm not going to do f in domain blah 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 like before. It's just arbitrary f. That is b tagged, whatever. F is a function from a check to z check. Boolean and f is a surjective function. You can write a check to z check. It doesn't really matter. Okay, equals to 0. Well, okay, this is literally equal. And so if I show that for all f, this business is equal to 0, then the Boolean OR of zeros is just 0 again. So we, in fact, prove this statement. Okay, so if I show that for all f, that is a B set, okay, this thing happens to be in B, is equal to 0, then I will have shown the desired want to show. So this is my goal. My goal is that if I fix, fix f, okay, I fixed Z and A. If I can show that this thing is equal to 0, then I'm good. Okay, then I'm good. Okay. Now, here is a theorem of ZFC. Okay, one that is in fact not too hard to show. For all domains and codomains, let's say, for all f, x, y, z, f is a function from D to C, and f of x equals to y, and f of x is equal to z. That implies that x is equal to 0. Sorry, y is equal to z. Okay. By the way, if you're uncomfortable with this notation, there is in fact another formula, much like is pair. Okay, I'll call it is eval parentheses f of x. Okay, so anytime you see sort of illegal notation, you can always replace it with just a sentence or an expression formula in the language of set theory. Okay, this is a theorem of ZFC, and so by one of the big, three theorems from above. In fact, I give it a name, soundness, by soundness theorem. The bracket of this is equal to 1. Okay. So what does that mean? That means that the Boolean and over A and Z, okay, F, A, Z1, Z2. I'm going to change the variable names because many of them are now B-tagged sets. Okay, so these are all B-tagged sets. Bracket is equal to 1. Okay, so this is a fact. Okay, so this is we know. This is something we know. Okay, so in particular, for any A, Z1, Z2, Z1 not equal to Z2, A and A, Z1, Z2 in Z, okay. If we expand out this business, okay, then we get that F is function from A check to Z check, and F of A check is equal to Z1 check, where again, we should be using that first order logic set theory formula. Boolean and F of A check is equal to Z2 check. this little operation, Z1 check is equal to Z2 check. Okay. Throw back to that exercise I assigned in part B, this guy. If we use that guy right now, okay, then we can replace this funny arrow with this. Okay, so I'm just going to do that. I have to go back through and, check that that is in fact what I applied. All right. And finally, we use that Z1 is not equal to Z2 here to get that this thing holds nowhere. Okay. This is again exercise. Okay. Okay. Yeah. So a hint for that exercise is think about this result that I talked about with bounded quantifiers. Okay. In fact, there are no quantifiers here, so that's fine. Okay. So this is something we know. Great. Let me define this quantity to be B. So this is going to be some B in B, right? Turns out we actually don't need to care about this. But this whole expression is equal to B and FA check equals Z1 check and another B. Okay, so just like in normal power set, if you intersect the same set twice, it's itself. In any complete Boolean algebra, in fact, any Boolean algebra, B intersect B is itself. And various commutativity properties of this operation allow you to rearrange it as I'm doing now. Okay, so we get this true fact. Okay, so this is something we know to be true. All right, almost there, almost there. Now, what do we do? This, by this, okay, we have shown that for all A and A, the set BA, which we define to be B Boolean and FA check equals Z check for Z in Z, my bad, which is a subset of B, hence the notation B sub A. These guys are all pairwise disjoint. Right, that's what we're seeing here. This intersect, this intersect this guy is equal to 0. Because this is true for all Z1 not equal to Z2. Okay, so again, stare at that a little bit. Hopefully you're convinced that BA is pairwise disjoint. Okay. All right, that was step 1. Part 2, we use the theorem from part C, this countable opens thing, right? Remember, these guys are R in B, which was equal to RO of 2 to the k times n. These are in fact open. Okay. And if I have pairwise disjoint opens, this shows that each BA for all A is countable. Good. Step 3, moving right along. I claim that for all A in, my bad, A, okay, only countably many, Z in Z. I'm going to call this set Z sub A, a subset of Z, which a countable subset of Z, is such that B Boolean and FA check is equal to Z check is not equal to 0. Is not equal to 0. And the proof is as follows. Suppose for sake of contradiction, okay, FSOC for sake of contradiction, uncountably many Z's in Z's, such that this holds. So let's pigeonhole. our pigeonhole friend comes back, hence its appearance in the combinatorics section of the talk. We have uncountably many z's and countably many um, in a countable BA. And so this shows that uncountably many z and z have the same B intersection FA equals z, which was non-zero, right? Non-zero. But then the intersection of any of those will be itself, which was non-zero, right? If I define this whole thing to be B tilde, then the intersection of any of those will produce B tilde again, which is non-zero. But this contradicts what we said above, which was that anytime we have two different z's, okay, these two intersections must be zero. Okay, so that's the contradiction. So again, stare at that a little bit. Step 4 out of 5. We're almost done. Consider the union. Union over A and A of Z sub A. Z sub A, which is a subset of Z, right? Its size is less than the size of each ZA, okay, which is countable by claim 3. Okay, each ZA is countable times A. But we said this was strictly less than cardinality of Z. So this die has strictly less cardinality than Z, which implies that there must exist some Z underline in Z. Okay, Z underline, element of Z, is outside the union. Okay, which by definition means that for all A in A, okay, B Boolean intersection FA check equals to Z check underline, okay? So Z underline referring to this guy there, that is equal to 0, right? That's what being outside the union means. Last step, F is surjective from A check to Z check is equal to for all Y in Z, there exists X in A, so that F of X is equal to Y, which by the definition of this bracket on these for alls and exists, that's Boolean and Z in Z, Boolean or A in A of F of A check equals to Z check. Okay, which is bounded by a specific choice of Z, right? The intersection over all Z's in Z's is bounded by what you see from one particular Z. Okay, so this is less than the countable intersection, sorry, Boolean intersection of this. Okay. All right. I'll let you think about how we end this. The finale is we bring back this expression up here. Okay. So what do we want to show? We bring this expression down. Oops. Okay. Remember, this guy was defined to be B. Okay. And this guy we saw was less than or equal to this. Okay. So this whole thing is bounded by B Boolean intersection, Boolean OR of these things. And using the properties of the Boolean algebra, which I did not say, but is true, we have this. Okay. And the final blow is that this thing is equal to 0. And the or the union of 0 is 0. So we have successfully shown this. Okay, that concludes the proof that the continuum hypothesis cannot be proven from ZFC. Okay, let me summarize the main sketch. Okay, so we have the soundness theorem says that if CH can be deduced from the axioms, then its value would have been 1. Okay, its value would have been 1. But we have in fact shown all of these pieces of the finale put together show that in fact the finale pieces show that in fact not CH holds with 1, which is the same thing as CH holds with 0. And so ZFC cannot prove CH, where we use the contrapositive of the soundness theorem. Okay. So hopefully this was an enlightening overview of the proof that ZFC cannot prove CH.